Okay, hello and welcome to this week's video, which is my last in my series of working through the problems of magnetohydrodynamics from Jackson's classical electrodynamics. We are on to problem number 7. Yeah, let's begin. Part A, right, let me read out the whole question first, then we'll go part by part. So the question asks us to consider the problem of waves in an electronic plasma with an external magnetic field B naught being present. It asks us to use the fluid model, neglecting the pressure term as well as collisions. And part A asks us to write down the linearized equations of motion and Maxwell's equations, assuming all variables vary as exp I k dot x minus I omega t. If there's one thing I've learnt from GCSEs and A-levels is that write down means it should be easy. So if we neglect thermal pressure, then T goes to 0, and also mu goes to 0. Nu. Assuming we're going to assume flow wave. So it's also obviously e to the I k dot x minus I omega t is just a plane wave. So, oh, sorry, app's opening on the computer and I didn't like it. We have our spatial derivative become minus I omega, of course, and del becomes I in the k direction. And so we get the linearized electron momentum equation, which should just be minus I omega v is equal to E over m E plus 1 over c v cross b naught. Cool. And also we just have Maxwell's curl equations. Note also, so this is 1. We have J is equal to N naught EV, our current density J, and so we get that I K cross E is equal to I omega over C B B1, which is our second equation, and then that's I K cross B1 equals to 4 pi and naught from up there E over CV minus I omega over CE. 3. These are our linearized equations of motion. And well, that was the equation of motion, and this is our Maxwell equation. Wonderful. I think it's fairly clear where these all come from. Although it's just blanked my head. Lorentz force law, and then Maxwell equations. But under these preconditions. Part B, which is the maybe not so easy part. Part B asks us to show that the dispersion relation for the frequencies of the different modes in terms of the wave number can be written as omega times omega squared minus omega p squared times omega squared minus omega p squared minus k squared c squared all squared is equal to omega b squared bracket omega minus k squared c squared bracket omega squared bracket omega squared minus omega p squared minus k squared c squared close bracket plus omega p squared c squared k dot b all squared. B is our unit vector in B naught. Omega p and omega b are plasma and precision frequencies respectively. Right. Let's take our above equations. This is part B. Usually it's a lot later in the video that I forget that I've written part A. We are going to substitute one of these into the other one. Probably 2 into 3. So IK cross C over omega K cross E equals to 4 pi n naught E over C V minus I omega over C E. And then we can rearrange for V. I'm going to put that in a square bracket. Cool. And I mean here we can just define this as the plasma frequency omega p squared. But this will be over m, so we can say this is, I think, fairly standard by now. I've got the p, 4 pi n o e squared over m. And we can multiply the momentum equation by 4 pi n naught e I over omega, which should get rid of some stuff. So 4 pi n naught e squared over mv is equal to e I omega p squared over m omega e. I'm not enjoying my positioning of my pen tablet. Plus 1 over c v cross b naught. That should be cross b naught. So omega p squared is it therefore omega p squared 4 pi n naught e I over omega v is equal to minus omega squared e minus I omega e over mc. Oh, will I have enough space? Put it down there. Let's see, 4 pi n naught e I over omega v cross b naught. I could probably have put that one inside a bracket. Cool. That's certainly one chunky equation. And now we can throw b in, and that should hopefully make things easier. And also the precession vector. So b is the unit vector along b naught, and the precession frequency omega b is minus e b naught over mc, which is minus omega b b. That's not very good omega. Nice. And that should make things a bit less. Oh no, actually it might not. We'll see. So that leaves us with omega p squared e plus c squared over omega squared k dot e minus k squared e is equal to, you have to write very small, squared e, so I omega b, I don't have space, oh, because I wrote this too big, what was I up to? Plus c squared over omega squared. Minus k squared e cross b. And we can get rid of some stuff. And then we should be able to collect terms and end up with the electric field response vector, which is v. So we should, yeah, which is omega squared minus k squared c squared e c squared k yeah, nice. This is our v. I forgot to say that. And that's equivalent to. So plugging this into this whole mess, we should have that v minus omega p squared e is equal to minus I omega, nope, omega p, omega v cross b. But we want to express v in terms of b, which, this is just a shorthand basically for now, because it wants us to give it in this stupid form. So we should actually probably take the k dot v and see what happens. So k dot v would be omega squared minus k squared c squared times k dot e. Which is just omega squared k dot e. Wonderful. So c squared k dot e is c squared over omega squared k dot v. That should be big V. So we now can shuffle some things and forgot all of the arrows that time. Is equal to omega squared minus k squared c squared e. So therefore e is equal to 1 over omega squared minus k squared c squared. That minus isn't where I want it. C squared v minus c squared over omega squared k v. Nice. Oh god, it gets a lot worse. Right. Okay, that's good. Let's get this back into our governing equation from before. So now it yields that omega squared minus omega p squared minus k squared c squared v plus omega p squared c squared k dot v is equal to minus I omega B omega squared minus K squared C squared V cross B from earlier. Wonderful. Yeah, I think we'll do coefficients. I'm not doing all of that. So alpha can be that one. Nice. Beta can be that one. And then gamma is minus omega B minus K squared C squared. Yeah, cool. So alpha V plus beta K dot V is I gamma V cross B. Right. What we're going to do is some vector algebra. To find the determinant condition, we will do some operations. So let's dot everything with B. So alpha V dot B is beta K dot B is 0 because that dot B is 0. And now we'll cross with B. So that's 1. It's going to be 2. Cross with B was that alpha V plus B plus beta K dot V K cross B equals I gamma V dot B times B V. Nice, and then 3. We will. Oh wait, no, we don't even need to. We can just get rid of some cross products. Because of step 2, we know that V cross B is 1 I gamma, sorry, alpha V plus beta K dot V. Wonderful. So if we take dot product with K, we should get that alpha minus gamma squared plus alpha beta K squared K dot V plus, I can't, I need to write small, alpha squared minus gamma squared plus alpha beta K squared. Okay, and K dot V is gamma squared K dot B V dot B is 0, and we can substitute in V dot B from this here, which will be that over K, which will get rid of that. and dividing by k dot v given it's not equal to 0, which it wouldn't be. From everything we get that alpha squared alpha plus beta k squared is gamma squared alpha plus beta k dot, that's not a k, k dot b squared. Nice. I don't think I can write all of this out again. But I mean, if you just look by inspection, you can see that what we're trying to get to is this. And all of it's squared, and all of that side squared. And I hope that then by looking at these three coefficients and this equation, you could see that this would expand to the full. I think it's the Appleton-Hartree dispersion relation. Don't quote me on that if it's wrong. But that's what I have written in my notes. That's certainly a lot of text and writing. There is one more part, however, which is part C. Part C says, assuming he loves just adding in these just extra bits, and it has part I and double I, of course. Assuming omega p is much less than omega p, solve approximately for the various roots of the cases. 1, where k is parallel to b. 2, where k is perpendicular to b. Sketch the results for omega squared versus k squared in the two cases. No, I'm not gonna sketch anything, I'm just gonna talk. Actually, I'm going to start there because we have the equation there. So take I, k dot b is k in this scenario, so the bracketed term at the beginning is omega squared minus omega p squared, omega squared minus k squared c squared. That factorizes globally. So we have three modes. One where omega squared is equal to omega p squared, which is a longitudinal plasma wave unaffected by b naught. 2, where omega times bracket omega squared minus omega p squared minus k squared c squared close bracket is equal to plus or minus omega b bracket omega squared minus k squared c squared, which is our second solution. This defines the transverse right and left circularly polarized waves. At high frequencies, they split. So if omega is roughly equal to ke, you would see that omega squared is roughly k squared c squared plus omega p squared plus or minus some things. At low frequencies, the negative branch would create this kind of whistler mode, which is very dispersive. I guess a sketch would just be of omega squared versus k squared, flat line at kp squared, and then two curves originating from there that are asymptotic to k squared c squared. Yeah. And then there's case 2, which is where k dot b equals 0. And again, we have two distinct equations. We have an ordinary O wave, which is linear polarized with E parallel to B naught. This is identical to just an unmagnetized plasma. And then part 2, we have this extraordinary wave, X wave even. It has this resonance where K tends to infinity. There's an upper hybrid frequency as well, which is omega p squared plus omega b squared. And a sketch would be straight line. The gradient would be c squared, originating at omega p squared. And then there'd be a lower branch which would start below omega p squared and flatten out at the upper hybrid frequency squared. And then there will be an upper branch which originates above omega p squared, and that would run parallel to the O wave, which would be for our X wave. Apologies, that was not yawning because this was incredibly boring. Although you may feel that way after all of this blabber. I'm not sure whether I'm happy that I've finally finished this saga, and it does feel quite like a saga. I guess I ought to put a box around this. What I might do is copy down what alpha, beta, and gamma were, so that I can at least pretend that I bothered to write everything out, and I didn't actually. And I'm totally okay with that. I think that's completely permissible. All of that can definitely go in a nice big box. Well, anyway, that was that's Classical Electrodynamics chapter 10. I'm probably not going to upload more textbook questions because it gets quite monotonous. I prefer to look at specific physical characteristics and try and derive this mathematically. But don't take my word for that, because I might forget how painful this was, and then do more of it. And also at some point I'll be in uni, and then there'll be lots of textbook questions that I have already solved that would be very easy to just throw on here. I like putting effort into, a little bit of effort into these videos. But anyway, I hope that was enjoyable, and I will see you next week for something new. Goodbye, and have a nice week. Goodbye.